and ocean interaction. So he used a combination of coupled climate model, observation, and simple conceptual model to understand the ocean's role in the Earth's climate. In January 2025, so about a year ago, Dr. Ali Siddiqui earned the PhD on salinity variability in the Subpolar North Atlantic at Johns Hopkins University with Professor Tom Payne. So as many of you know, here we have very, very active research on North Atlantic circulation, Arctic Ocean circulation transport, and AMOC, and this department and the department, next door, the geoscience. Not to mention, the remote sensing, right, which started here. So it's perfect time to invite Dr. Ali Siddiqui here to introduce some new ideas and also stimulate some new research direction and collaboration. Now, Dr. Ali Siddiqui, the floor is yours. Let's welcome Ali again.
Thank you. Thank you, Fang, for that awesome introduction. Thanks, everyone, for coming in today. As Fang said, I am going to be talking about some things from my PhD and some new stuff from my postdoc, which I'm more excited about right now. So, just one thing to know before the presentation begins. There's going to be some furry creatures in the presentation, so if you guys are not expecting some furry faces, then just a lot of caution. And yeah, I'm just going to get right into it. So, I'm going to first talk about the subpolar North Atlantic. And what's so special about the salinity here, which is what I've been thinking about for almost 6 years. And I'm just going to leave this here for about a minute, so we can all look at this amazing visualization, which is showing us in a very conceptual way of warm salty waters on the surface in the North Atlantic that make their way towards the Iceland Basin, south of Greenland, and they supposedly get colder, denser, sink in this part of the world. It is not a complete picture, but that's kind of like the idea behind some of the, I guess, Climate 101, when you think of overturning and the AMOC, and it's kind of like the big picture of that. The idea being that there is some kind of water mass transformation that's happening in the subpolar North Atlantic region. It's this really special zone where we go from the alpha oceans to the beta ocean, which is where the density is controlled by temperature effects, to density being controlled by a salinity effect. So there's this very special zone of interaction that's happening over here. And this is what I was obsessing for about 6 years. This is a very interesting, almost a painting that represents Wally Broker's idea of what the Great Ocean Conveyor Belt was, which we now think of as the AMOC. You can see that there's nothing to do with the Arctic here for some reason. And we have since developed more insight into how important the Arctic can be. But it's the same idea that in the low latitudes you have warm, shallow currents that kind of go throughout the world. And then at some point they kind of sink. There's some kind of water mass transformation, either in the Weddell Sea or in the subpolar North Atlantic region. So that's kind of like the motivation behind me thinking about that. This is another kind of slightly more detailed way of thinking about it. This is from a paper by Eleanor Fiker-Williams in 2023, where she talks about, if you look at a transect in the North Atlantic from south to north, you can see the movement of water masses in the top 1,000 meters. They're essentially going northwards, and at some point between 1,000 and 3,000 meters in that whole transect, you see kind of deep waters coming in from the north to the south, and then way at the bottom, what we call as Antarctic warm waters, below about 3,500 meters, you see them flowing northward again. And that's kind of like a slightly conceptual figure of what the overturning can look like. And then you can kind of go look at some more details of what that transformation might look like involving the Arctic now also. And I was just talking to Frank about this, how this interaction of what happens in the Arctic doesn't just stay in the Arctic. There is a sense of the importance of overflows, for example, where there is a lot of deep water that gets formed and eventually makes its way into the branches of the Atlantic deep water. And surprisingly, that's like a science question that some of you would want to maybe think about. Why don't we have a understanding of what happens to this water mass and how does it end up being part of the AMOG? And why is there not a lot of work that has been done? Does it have to do with observations? We can't really measure a lot of stuff in the Denmark Strait overflow. It's also not an easy place to model, even with high resolution DCMs. So that's a science question that I think I would be very interested to think about in the future. And also it's good thing to think about from how to make movies about the AMOG, because we obviously didn't get that right in 2004. The other reason why the AMOG, or not the AMOG, but things happening in the subpolar region are important from the standpoint of sea level rise. This is from a paper, I think, in Nature Climate Change, from Leon Schafik, where it talks about the connection between warm and salty waters and sea surface height anomaly. And it's kind of like playing on this idea of, the spiciness of the ocean, that warm salty waters can have a higher sea level, and it's kind of very obvious in this figure, but it's gone through a lot of averagings, and there's a lot of analysis, data analysis that goes into like making something as smooth as this. But the idea being that when you have decadal kind of periods of warm salty subpolar Atlantic, you can have a higher sea level in corresponding to Western Europe or North America, Greenland. So that's kind of also relevant. For me personally, the thing that motivated my research question was this paper by Penny Holiday talking about the largest freshening event that happened in the Iceland Basin in the last 120 years. And that's highlighted by that really big dip in salinity. And I was trying to chase down the mechanism of why that salinity drop happened. So in order to do that, started with something that I think a lot of you might be familiar with, that is the echo state estimate. At the end of the day, it is an estimate for a reason, because even though there are a lot of times we think of echo as like analogous to observations, but it is a TCM that is trying to resemble observations. It is doing a very good job at it. And so at some point, even when you're working with echo, you want to make sure that you just don't take for granted that it's going to look like observations. And I'm going to show you an example of what that really looks like. And for those of you who are not familiar with it, there's a time period of about 30 years that we're going to look at. And this kind of figure is from the echo documentation. The way they do it is like put it up into like 13 different tiles. But that's not the most important thing. The idea is that it's also like a 1 degree resolution model, which is kind of on the order of what usual climate models do. There have been now LLC 1080 for 320, so very high resolution MIDCM runs, not always data assimilated though. And the other thing which I tried to do was look at observations as well, similar to what Penny Holiday and her colleagues were using, which is the EN4 data set. I do want to highlight that data products in oceanography can look very sparse. I'm sure a lot of atmospheric scientists over here know that. That's the difference between 1992 and 2017 of the distribution of Argo flows, essentially, and a combination of different hydrographic observations. This is from the manual of EN4. If you've ever opened it, it looks like they have a very, unfortunately, not a good-looking figure, but only up, after like 2007 is when they call it a global coverage of, in every 3 degree by 3 degree box, they have for each month available observations. So that only happened in like 2007. Which means that when you're working with EN4 or the Met Office data set, there's not a lot of meaning when you're looking at like 1950s or whatever and trying to look at area averaging stuff or trends. So what do we find? This is the time series of the upper 1,000-meter salinity volume averaged over the subpolar North Atlantic. The black line is showing the ECHO state estimate, and the red is the EN4 data set, taking anomaly for the whole time period of 1992 to 2017. And you can see that the general trend is still kind of observed here. And the other thing is that EN4 shows way more variability in the time series. The other way to kind of like look at it is look at spatial trends of the salinity. So if I look at this freshening period of 2005 onwards, it does capture to a certain extent the freshening that's happening in the subpolar region, and including in the eastern subpolar North Atlantic. There's a lot of kind of variability that's not captured, but fortunately, that's maybe how the experiment is designed. I'm not looking at, say, for example, the Labrador Sea in this question. So how do we go about establishing that ECHO does a good job? One of the ways is by something called as Ocean Spy. The Ocean Spy is a Python package that one of the other PhD students in our lab developed. The idea is that can you figure out a way to make our ocean models pick up data just like observations do. So can we make like a survey station, just like a hydrographic station? And that's kind of what Ocean Spy does. And that's what I try to do with this kind of region of interest. That's the eastern subpolar North Atlantic. And that's the kind of comparison between a ship-based measurement in 2016, the summer of 2016, for the OVID line with ECHO. And I'm going to let you guys decide what that looks like. But as far as I was concerned, this is good enough. How do we define good enough is a very subjective term. But without trying to interpolate them to the same grid, we can say that it does capture some of the water masses that are present along the OVID line. And that's kind of what I told myself, that they both look the same. So ECHO does a good job, I think. And you can do that for another hydrographic kind of line called the Elliott line that's also had long-term observations, and kind of also does a reasonably good job. Just to remind ourselves that ECHO is not going to capture exactly the model, it's not going to capture observations one-to-one. Because we're still going to make sure that the model is conserving volume, heat, salt. That's the thing that ECHO is supposed to be doing. We can, though, look at these two kind of events that happened. So in the early 90s, and then in the big event, the 120-year event, 2012 to 2016, and look at the spatial maps of these anomalies. And you can see that ECHO does capture the 2016 kind of finale of that salinity anomaly in the eastern subpolar North Atlantic. What the Holiday paper was trying to do was essentially create these maps and take a guess for what was happening. Where do these anomalies come from? We can do that too with just looking at it. But this is just to illustrate that you can't really say, is it the subtropical waters coming in? Is it the Arctic fresh water? Is it the AMR? What's going on? We don't really know. So the way to kind of move forward is a bunch of different ways. The way I tried to do it initially was to create a kind of a Eulerian kind of Lagrangian pseudo method to follow salinity anomalies. Again, the reason I was able to do that is because Ocean Spy helped me create a section, an artificial section in ECHO. So I can now have a section that goes all the way around the subpolar gyre, and also gives me a section which goes along the Gulf Stream, and then I can follow those anomalies. So the first kind of figure, the Hogg model, which shows time versus distance along the cross-section, is giving me an indication that there is some form of propagation of these Salinity anomalies across these sections. Although it doesn't really give me anything more than that. It gives me a velocity, it gives me a time scale, and that's for the path along the Gulf Stream. What it gives me an indication is that there is a lot that is being done by these kind of Western influences into the Asian basin. So already we have some indication of that. There is a lot of propagation of these anomalies being carried out by either the Gulf Stream, the changing of the NAC, or it's happening because of the circulation around the subpolar North Atlantic. So the next thing that we really try out, it gives us a good sense of what is happening in terms of mechanisms, is conduct a salt budget. And that's what essentially you use things like echo state estimates for, where you can quantify a rate of change of the salt in terms of advection, diffusion, and surface forcing. And that's a security equation, which is the volume and time integral of just those terms. So what do we find? We find that if I look at the whole time period, the top panel shows the entire subpolar North Atlantic, and the bottom panel shows me just our region of interest, that's the eastern subpolar North Atlantic. And this follows very much from the work that Chris Pikelts did in 2017, and before that Martha Buckley also was doing budgets with ECHO. And so a lot of inspiration from their papers. The idea being that the top 1,000 meters of the salt budget is explained entirely by the advection term. And so not a lot being done by diffusion or kind of surface forcing. This is for the top 1,000 meters. And if we then decompose the advection term into the Eulerian or the resolved terms in ECHO, because it's a 1-degree model, versus the bolus term, which is essentially GM parameterized terms, we find that this is where the thing becomes interesting. The first part of the time series, which is this gray thing, which we want to explain, most of that is being explained by this black curve, which is the Eulerian time series of the anomalous circulation. Whereas when we get to the end of this time series, the anomalous circulation doesn't really play a role. It's the mean circulation carrying anomalous salinity that is causing. So especially this big freshening event, it's surprisingly how clear that signal really comes out in especially the eastern subpolar region. We can also do another kind of decomposition into transport across boundaries of east, west, south, and north. And what we see is that for the 2012-2016 event, most of that transport, unsurprisingly now, I guess, is coming from this western boundary. And that's kind of the extent of the salt budget that I did. There were some questions about why not salinity and why salt. There's some very slight differences. In the salinity budget, you do have D-C terms, which can be quantified separately. We still don't really see the impact of that, which dominates over, say, the diffusion term or the advection term. And so we end up concluding that the freshening events, both of the F1 and F2, as we call them, are driven by changes in the advective convergence term, and the freshening of the 90s occurs due to the anomalous circulation term of the mean salinity field, whereas the freshening of the 2010s occurs due to the mean circulation of the anomalous salinity, and it's happening entirely due to transport across the western face of the Asian basin. And that surface fluxes play a minor role relatively in both cases. So that's what the subpolar story was about, and that's kind of where I'm going to leave that for a second. And then kind of move on to some of the Arctic stuff that I've been doing recently. And I've been thinking about the surface kind of heating of the Arctic Ocean. That's the first furry animal, that's Olivia, she's 19. And what's so special about the Arctic? Well, we're going to see another video by amazing NASA visualization studio. So props to NASA for doing all the great stuff that they're doing. That's the sea ice area in million kilometer squares. That's how we like to represent that. And most of you probably know where we're going with this, that the sea ice area, since we've had the satellite record, has gone down considerably up until 2025, especially with like these rapid sea ice loss events in like 2007 and 2012. There is this idea that we have that maybe something like stabilizing here, but not really, because like this year itself was the second lowest sea ice record. This does not go to 2025 though, this is 2024. So what's the implication of this on the surface energy budget of the Arctic, and specifically the shortwave term, because I'll get to why that is. Before that, just to answer the question, the other reason why the Arctic is so important in kind of climate studies, this is a paper from Mark England and colleagues from 2021, a very nice figure. I really like this figure very much because it talks about the relative amplification of Arctic surface temperatures compared to global mean of the order of between 3 and 4. And the same has been hypothesized in experiments of, like, in this case, 4 times CO2 by the very famous paper from 2014, which, by the way, for those of you thinking, the third figure is not their best figure. This is the first figure in that paper. You can see that the y-axis is like 20 degrees, that's insane. But remember that these are 4 times CO2 experiments. Still, they can show the seasonality of that warming and also the amplification of about 4 times in the Arctic. So kind of seeing that in the observations also. So coming back to the meat of the talk, which is like sea ice albedo feedback, is the thing that I'm concerned about in terms of the impact of sea ice going away. What is the sea ice albedo feedback? It's a positive feedback wherein you have a mismatch in the surface albedo of the ocean and sea ice that leads to kind of more increased solar absorption at the surface, leading to more increased sea ice and more warming, and that kind of completes this positive feedback loop. At the heart of the sea ice albedo feedback is the albedo of the surface and the solar radiation that's being absorbed by the surface. That's figure number 2 from Eaton and Morrison, where they use CMIP5 models to show that the albedo feedback from a top of the atmosphere perspective and also from a surface perspective is a important, either the most important or one of the most important mechanisms for Arctic amplification, which is also seen in the CMIP6 models. Now, all of these studies are looking at this kind of radiative kernel mechanism where you figure out the perturbation in albedo at the surface and look at top of the atmosphere radiation budget. However, there's a much simpler kind of way to look at it, which we'll get to. The things that we don't understand, the impact of clouds, because the Arctic is one of the most cloudiest places in the world, and how much do we expect the clouds to oppose this albedo feedback is unknown, and the impact of sea ice albedo itself. And that's kind of the mind-blowing thing when I was looking at this, is that a lot of the papers, especially by Don Perovich, that have really, tried to explain a lot of the changes happening in the Arctic surface energy budget. For example, like this 2007 paper that looks at the impact of sea ice cover decrease in 2007, being led by this kind of sea ice albedo feedback, specifically because of more absorption here in the Beaufort Sea. It does not it kind of neglects the albedo of the ice itself changing, and it's just like looking at the albedo of the ocean versus the ice surface. So what do? We go back to the fundamentals. We look at this. That's what the surface heating should look like. If you rewrite the albedo of the Arctic, that's a combination of sea ice concentration, sea ice albedo, and the open water albedo, which we're going to assume to be constant. And then we can kind of apply the most basic fundamental thing that we've all done in grad school, which is doing a time mean and perturbation for each of the terms, and then solve for the anomaly in solar heating, and you get an equation like that, which has a lot of terms, but you probably know all of them. And let's go through them one by one. That's the first term which you all know. That's the change in sea ice area, so C prime. That's the term that's changes in sea ice albedo, and that's the term changes in surface shortwave flux. So we have these three first order terms because of changes in the ice area, ice albedo, and the amount of surface radiation reaching the surface. And then you have a bunch of second order terms like the covariance between all of these three terms. You also have a third order term if you make sure to account for every term. Now, how do we compute these? We can use models and observations. That is a art piece of the NCAR building, the MESA lab, which is in some trouble right now. But they produce some very fascinating, amazing model output for all of us to look at using the Lens 2 data set, which is essentially historical and a certain future kind of radiator forcing term from the middle of the road. It has 100 model realizations, and it has a really long time series. You can also do Lens 1. The thought behind that is that using a CMIP5 kind of version of model and CMIP6 version of model, very similar except that you have changes obviously in the albedo parameterizations, cloud parameterizations, the number of ensemble members is also lower, and it has the quote-unquote worst-case scenario. And then just to make sure that the models are not hallucinating, like the LLMs, we also want to make sure that we evaluate our analysis against observations. That is a time series of a monthly summer mean, so May, June, July, August, sea ice area for Lens 1, 40 members, Lens 2, 100 members, and observations. It is now well known, well, this is not the first time someone's seeing this figure, but Lens 2 underestimates very much the sea ice area, and that's kind of was the reason why I was thinking about all of this in the first place, why the CMIP6 models get the sea ice area wrong. Lens 1 surprisingly did a relatively okay job if you think about the 21st century, but it still has biases in the 20th century. Scary looking thing is that observations have seemed like a higher rate of decline in sea ice areas compared to Berkeley's. Now let's look at all of those terms one by one in both Lens 1 and Lens 2. What I'm doing is I have a 3D field, take an area average, and then look at time mean and time anomalies. So that's what the sea ice, that's what the classic traditional sea ice albedo effect looks like. And that's a non-zero effect of change in sea ice albedo itself, which is going to be the crux of this whole paper. Surface shortwave flux leads to cooling at the surface, which is not surprising. You have more clouds, so you have less amount of shortwave radiation reaching the surface. And then you can kind of sum up the other second and third order terms and get the net solar heating. Another way to kind of like just look at this from a seasonal perspective is for both Lens 1, the first top panel, and Lens 2, the bottom panel. We can look at the effect of, we can stack these three terms month by month and look at effects of ice albedo change, ice area change in the red, and then short wave, which can also be decomposed into short wave that's changing over ice surfaces and ocean surfaces. And you can see where I'm going with this. Clearly, changes because of ice albedo do have a huge impact, if not more than even equal to the ice area. In the lens one, there are certain months like June and July where they're even higher than the ice area changes. Those are defined for 2 different periods. So 1980 to 2020 is like a historic period, and then 2020 to 2060 is kind of like a future scenario. And takeaway one, future warming because of ice area plus ice albedo is about 2 to 4 times by mid-century. Changes in ice albedo contribute significantly to the net, and clouds have some impact in producing cooling over the ice surface and the ocean surface, but more so in lens 2 and less in lens 1. And now we can try and see what the observations are. So this is from the APPX data set, which I just realized that it's made here in Madison. So that's amazing. And you can look at the time series for the last 20 years, from 1982 to 2024. This shows 2021, I think. But this is the amount of solar heating because of changes in the sea ice area term. You can see that there is a relative increase, about 10 watt per meter squared. Changes in sea ice albedo going way up. So even in observations, we do know that the amount of solar absorption is high compared to ice area change. What's very interesting also is that there is not a lot of changes in the surface reaching shortwave flux. If you take an integral throughout the Arctic, there is some things happening here after 2008, but overall, not a lot of decrease. So in order to kind of like think about what are these biases, looking like the changes in sea ice albedo as like a relative fraction is shown here as a time series for lens 1, lens 2, and the observations. Surprisingly, the change in the albedo term looks similar in all three. And this is a deceptive figure because this is not showing you absolute values. Absolute values, there is a mean bias, so that's being removed here. The figure on the right shows the sea ice area term for observations, which you've kind of seen already. But you can see that the rate of kind of decline of sea ice area is kind of all over the place for lens 2 versus lens 1, which kind of really goes down later on because it's a higher RCP scenario. And the observations is just like doing something even more crazy. Now the idea behind doing changes over ice or changes over the ocean is that because we've been so obsessed over thinking of the change in sea ice area as the driver of sea ice albedo effect, so once we kind of start integrating the effect of clouds into it, then we can have these kind of two terms. One is changes because of ice albedo plus the shortwave forcing over ice, so that's all the ice terms together. And then the traditional kind of open ocean sea ice albedo effect plus the shortwave effect over open ocean. So you have ice kind of changes and ocean changes, and you can see what those look like in observations. Most of the solar heating seems to have happened over the ice surface, and it relatively equal happens in July, August, and May over the ocean. And so that's kind of like the big picture message for most of this analysis. The other thing that we can kind of look at in terms of changes in the melt season, for example, is how much cumulative solar heating is happening at the Arctic surface. In the models, this is, so each bubble represents a single ensemble, and changes over ice and ocean are depicted versus also separating out the impact of clouds. So this kind of like helps us put into context that lens 2 clouds have a more kind of cooling effect than lens 1. And that's what observations look like. So obviously there's more kind of variability in the observations, and what we see is that you can try and fit those observational points somewhere on either lens 1 and lens 2. This is what I try and do here. This is a figure of cumulative heating on the y-axis for the whole summertime versus the ice area. And then all those points show ocean versus ice for that's lens 2 and that's lens 1. And what we see for observations now is that that cumulative heating over the ice surface resembles more of a worst case scenario. Also for the kind of traditional changes of the ocean resemble more towards lens 1, although there are like points that definitely lie on lens 2. So this kind of like get a sense of what the observations are really doing, which is obviously not here or there. That's basically it. He's 2 years old. He was surprised as well when he looked at these. And then the last thing I want to talk about today is we can then start thinking about this from like a parametric relationship. We now have these three, dominant kind of terms: ice area, ice albedo, and surface shortwave. If we plot those three terms as a function of sea ice area change, so 1 just means that this is 1982-2002 average. And 0.4 means relative to that mean, 60% has gone away. The net, which is the gray line, that's the total solar heating that is actually happening at the surface. The blue is the one that is usually talked about in climate models. The red is the heating that's happening because of ice albedo changes, and then the clouds are cooling, masking what's happening with the albedo changes, basically. And that's something that's kind of missing in the discussion. This is trying to put kind of a context to the observational values averaged over the whole 40-year period versus the envelope of the lens 1 and lens 2. So the left-hand side is lens 1, right is lens 2. You see that observations are mostly captured in the spread for both lens 1 and lens 2, but obviously not for clouds. The cooling effect is seen in both lens 1 and lens 2, not so much. In fact, there's like a slight positive for observations. And so it kind of like ends up happening where you see lens 1 envelope resembling, containing the observational mean, and lens 2 just not capturing as much solar heating. Which is unfortunate because lens 1 is the old version and lens 2 is the new version. So we do then end up taking another kind of look at that. How do we quantify it in terms of what to expect in the future? If you just take the slope of these curves, which is the Q prime by sea ice area, and do a little bit of math, you will see that you end up with a term which is essentially the same as the albedo. When you write down the energy equation, the energy budget, you're essentially writing for an albedo term if you take everything on the right side. And what you can do is that you can create an effective albedo, assuming everything else remains the same. How much of the albedo is being represented by simply ice area changes. So for example, this blue line means that you have a higher impact of ice area changes as the ice area decreases. Why is it not constant? It's because there's more intense sunlight that's reaching higher latitudes as the ice area retreats. Ice albedo, on the other hand, there's less ice in itself, so there's less impact now. It's more obvious in lens 1, less obvious in lens 2. because not all the ice is disappearing in lens 2. And you can see the negative effect albedo of the clouds. In lens 1, it's not, it's kind of like relatively small. And if in those terms we look at the effective albedo of the observation versus the kind of envelopes now, this tells us that models are capturing the CS, the traditional CS area effect higher than what it really is happening. It tells us that lens 1 thinks too much ice is melting and there's too much contribution, whereas lens 2 is doing this kind of compensation of too much clouds and too much area effect, and so that's why somehow it gets this right. The net effect is that lens 1 has a super high kind of albedo effect that it thinks is happening, whereas it's not. So you can kind of like reframe the effect of all of these changes in terms of like this kind of non-dimensional number. And that's kind of like where I'm going to end with most of the Arctic work. Take-home message for that is that the traditional CS albedo effect is missing the albedo of the ice itself changing, and it's kind of like a good reminder that it's not just the contrast between the ocean and the ice, but it's also what is the albedo of the ice itself is changing. It's more melt ponds. It's not the same snow. It's less multi-year ice, and so on and so forth. And that's kind of like all the things that I already spoke about, and I'm just gonna stop over there, and that's it. Thanks.
Yeah. So we will start question from the students here. Are there any questions?
Thanks, Ali. I really like the way that you're doing that budget and sorting out those different terms. One question that comes to mind that I'd just like to hear a little bit more about, because I don't know, is how these models are parameterizing that albedo. Like what goes into that, and how realistic are they? What would just be done to improve them?
Right. Short answer is go to the CSM tutorial,
Yeah.
and they'll tell you more in detail. The things that I understand is that, so there's two parameterization changes fundamentally. There's a cloud parameterization, cloud droplets. In lens 2, you look at that 2020 paper that Gokhan wrote, it talks about implementation of this club scheme that is different in lens 2 than lens 1. In terms of albedo parameterizations, there's more layers in the sea ice that's being used compared to lens 1. And they've also, kind of, if I'm correct, again, it's based on my knowledge from the tutorial last year, that the way they write down the parameter, like the values that are given to how much, for example, our snow versus our ice, those are different. There's obviously way more changes that they've made, but that's what I remember at the point. Yeah.
Do you know if they're parameterizing melt then? Like
Yes,
okay.
they do. Absolutely. There are more melt bonds in CSM2 than in CSM1. And I think there's more people in the audience who know more about that, but that's what I think.
Yeah, I had a question about like penetrating solar radiation.
Right,
through
yeah.
the ice and whether that's also like
Yes.
parameterized.
There's a term called FS2 in model diagnostic, which comes out as the term that's beneath the sea ice. And I can actually show you. That's the shortwave budget that you can compute for both lens 1 and lens 2. Obviously, this all is messed up right now, but you can close the shortwave budget of just the surface layer without the FS2 term to a relatively okay accuracy. I'm also only concerned about the surface and not subsurface. That is supposed to be future work. in terms of where is that heat going now? Like Mary Louise talks a lot about how that is possibly affecting the heat storage in the halocline in the Beaufort Sea. You can also make an argument that eventually that changes the amount of spiciness of the Arctic. That's another paper of hers. Yeah, I'm like really reading a lot of her papers right now. But yeah, she's the expert. There's a preprint out there if you want to check out, which is I think submitted to GRL. It's talks about CMIP models, looking at how much of that penetrating shortwave is represented in the CMIP models, and that's the only work that I know of from like a couple of climate models. But yeah.
Hey, thanks for a really amazing presentation. My initial question was going to be about meltons, but you just answered that with different models. So I'll change it to a different one, which is we look at the atmospheric budget of the CAs. Have you thought of, well, on surface, have you thought of looking at the CAs processes, heat budget, which is involved in the atmosphere to see if CS and 1 and 2 have different CAs formation or looking at snow contribution and something?
Right, I had not looked at that yet. No, I did not. I went as far as looking at, if you look at the entire energy budget, the surface energy budget, you have your longer term sensible heat, latent heat. There is nothing interesting happening there, unfortunately, because the seasonal cycle of the shortwave in the Arctic is so large that like long wave is about like 50 watt per meter squared on average, doesn't change much, and latent and sensible are always less than 10 watt per meter squared. So even if you really try hard, not a lot of energy exchange is happening compared to shortwave. So I just stopped there.
Okay.
But yeah, I haven't looked at CIS budget. I want to do that with the latest Echo version. Compute the CIS budget and look at the terms, because now they do, in the latest release, they do CIS adjoint. So now you have the right terms as well. So stay tuned.
Okay, let's open it up. So I have one question actually. This is the first time actually I realized the albedo itself actually will change in the future due to more snow or more meltdown. This is really interesting. So we know probably there will be more snow and also more melting. So which kind of a mechanism, the change actually is more.
Yeah, competing. Yeah, at least in the models it says that there's more melt-on impact, because even though if there's more precipitation and more fresh snow, it's not enough to counteract the amount of melt-ons. It does remind me of, there's a whole literature of terrestrial snow albedo feedback, where they take into account the changes in the snow surface versus snow metamorphosis that's happening. For some weird reason, they don't want to do that on the ocean, and that's kind of why I feel like we're doing it. There's a lot of papers, like in the last 15 years, you'll see it, and they're all like written the same way, that, oh yeah, there is a change in the snow albedo, but just on land. I think partly because it's difficult to like measure CS albedo from satellites. Although the data set that I use, you can do that. Like they could do it before. So yeah, it's slightly confusing why that was not done before. Or I'm listening completely wrong. This is going nowhere. But yeah, there's a paper by Marika Renka. She does look at CMIP5 models and looks at a similar thing. So there's a big spread in the change in albedo over the 21st century. And a lot of stuff from Patrick Taylor as well. He does a lot of CMIP albedo analysis. All of it going down. So it basically means that more meltons than more snow.
Yeah, super interesting. Thank you. Just zooming out a little bit, I was wondering, and maybe I should know this, but so the lens 2 generally has, less CIs than lens 1. Can you talk a little bit about how much you think that is a change in the CI situation or a change in the background climate? Like, is it because,
Right.
is it the same CS physics? Largely, but
Yeah.
it's mostly a response to a different
Or
climate
the
state?
scenario,
Or,
yeah.
or
Yeah.
is it the background climate is the same, but CSM2 has a different
I think it's
sensitivity?
both of those things are happening because lens 1 is RCP 8.5, and so it's a different forcing in the first place. Whereas lens 2 is SSP 370, so it's not too different. Like it's a 7 watt per meter square versus 8.5.
And lens 1 is 8.5,
yeah,
so it's more forcing.
exactly, and that's the unintuitive thing that there's still more CIs in lens 1, so that explains the part that they changed a lot of physics in CSM2 to make sure to kind of like compensate for the biases that are happening in CS, and that's kind of what this stuff is happening. So this is from the 2020 CIS, the CMAP 6 paper. This thing over here, that is the kind of underestimation, or sorry, overestimation by models, which it seems like CSM2 was trying to focus on, and got it like overcompensated, whereas things are fine relatively for some reason before 2000. So there's definitely like a big impact, I feel like, more probably of an impact of the CI's physics itself than the scenario in this case. So, yeah.
Could you run simulation where you take the same CS model and
Yeah. That's why I went to the tutorial to learn that, and I'm hoping to do that. Like, if I have more funding next year. But yeah, that's the cool question. Yeah.
Well, let's first about the first part. Thanks for nice talk. So at the end, you concluded that you're seeing that big freshening anomaly in eastern subpolar North Atlantic due to advection due to what's coming through the western wall of the Icelandic basin. As I remember that holiday paper, they suggested it was coming out of the Labrador Sea from Canada. Is that the same kind of conclusion that you're reaching? Or does anyone else come up with anything actually paying much attention to that literature?
Yeah. So one of the reviewers in our paper, and they identified themselves, Alan Fox, was saying that you could try and make your box the subpolar box, the Labrador box, and see if you see what the holiday paper does. We said that our bigger box, the subpolar box, kind of could be used as a proxy for that. And the conclusion we were trying to draw was that holiday et al. Say that there is a lot of what they use like Arctic cooled Labrador current waters that move their way because of changes in the gyre itself. Like the gyre is modulating that, and because our analysis does not differentiate properly between what the gyre is doing versus what like a large-scale density-driven circulation is doing. So I can't directly answer that question. What is clear though that there is no like surface forcing that's doing it, which is what their analysis does suggest. So they were saying that about 10% of the freshening is because of higher PMIC. Yeah, we did not do the uncertainty kind of stuff though, so I don't want to comment on that, but yeah. Ultimately, Alan Fox, who also wrote a paper about that, said that they were partially in agreement. Partially in agreement with the same mechanism that there is a advection of these anomalies west of the Iceland Basin that are eventually propagating. How do those originate? We didn't say. and they say that it's water mass transfer means there's more surface cooling that happens in the laboratory 2 years prior, and that causes a lot of cold fresh water that ends up then coming to collection basin 2 years later. So in terms of time scale, that makes sense, and usually how a lot of folks talk about the surface cooling because of the NAO. That's kind of the ballpark argument, but
So that was Holiday, if I remember too, I think they also tried to make that.
yeah. But I was less convinced of that because most of it was just based on looking at maps and
Yeah, I remember that being a
yeah.
little shaky too.
Yeah. So yeah.
Cool. If we don't have more questions, let's thank Ali again.